Welcome. In this session, we'll learn one more approach of this convolution that's called the linear approach. So, convolution is defined as y of n is a convolution between two sequences, that's x of n and h of n. In terms of sum, we can express it like this. Now, in this session, we'll learn how do we evaluate this convolution sum using linear approach, and I will illustrate it two ways. Now, what we do in linear approach, we express x of n as a weighted sum of delta sequences. So we will express x of n as weighted sum of delta sequences. Sum of these delta sequences, and suppose to illustrate this, let's take the example of this x of n as 1 comma 2 comma 1. So this is our sequence, and this is our n equal to 0 point. Now to get this sample point, we saw this last time. If we to get this sample point, what we do to obtain the sample point of x of n, we simply multiply x of n with delta n. Same way, to get this sample point, we multiply x of n with delta n minus 1. Same way, to obtain this sample point, we multiply x of n with delta n plus 1. So we write it like this: x of n delta n plus 1 plus x of n delta n plus x of n delta n minus 1. So this is how we resolve our signal, and we know when we multiply x of n with delta n plus 1, it gives us the value of the sequence at n equal to minus 1, and this gives us the value of the sequence at n equal to 0. Same way, this gives us the value of the sequence at n equal to 1. So this is our, and if we substitute the values of this, x of minus 1 is 1, so it will be simply delta n plus 1. X of 0 is 2, so it will be delta n. Same way, this will be x of 1. X of 1 is 1, and that will be simply delta n minus 1. So this is how we resolve x of n sequence in terms of this. Then we say our input to the system is this. So input to the system is this, whose impulse response is h of n. So we say input to the system is this x of n. Then the output is of this system whose impulse response is this will be equal to. So y of n will be equal to. So when you write y of n, what will be y of n? Whose input is x of n, which is expressed as, so this is our x of n, which is expressed as a linear sum of these delta sequences. So how do we write the output? So the output will be simply the corresponding output to these sequences, corresponding output to these. So what's the output corresponding to this? So this output will be simply h of n plus 1, as we assume that the system is linear and time invariant. So output to this will be simply 2 times h of n. Similarly, the output corresponding to this will be h of n minus 1, and taking the sum of these individual response will give us y of n. So this will be our y of n. Okay, let's see this graphically. How do we obtain this graphically? Let's do that graphically. Let's do it step by step graphically. So our x of n is this sequence. So this is our x of n. X of n is 1, 2, and 1. So this is 2 at n equal to 0, 1 at n equal to 1, and 1 at n equal to minus 1. 1, this is 1, this is 2, this is 3, and these sample values are 0. So this is our x of n. Now to apply first, what we'll do, we'll apply this as the input. Now to obtain this, what we do, we multiply x of n with delta n. So the output of that multiplication will look like something like this. So this will be our output. So the output of that multiplication, so this is x of 0 delta n, which is same as x of n delta n. So this is the output. The input to the system is now this. So this is 2, and the rest of the sample points will be 0. Rest of the sample points will be 0. So this is the input to the system. And we know from LTI system theory, the corresponding output will be simply corresponding output of the system whose impulse response h of n will be simply, so if this is x of 0, it will be x of 0. What is the output for h of delta n? That's h of n. So the output will be, so we can write the output as, so the output will simply be, this is our x of 0, h of n, and x of 0 is 2. This will be 2 times h of n. And what's our h of n? And let's suppose the h of n for simplicity is 1, 2, minus 1, and 2. So this is our output. So you can write h of n like this. So this will be 2. 2 times 2 is 4, right? Because h of n is, let's suppose this is the value at n equal to 0. So this is 2. So 2 times 2 is 4. Similar, the value at n equal to 1 is minus 1. And when you multiply that by 2, that will be minus 2. Similarly, the value at n equal to 2 is 2. So the value will become 4. When you multiply 2 by 2, that will be 4. Similarly, the value at n equal to 3 is 0. So this will be 0, and so on. Now the value at n equal to minus 1 is 1. So when you multiply it by 2, it will be 2. So this is the output when the input to the system is x naught delta n are simply 2 times delta n. So if the input is 2 times delta n, output is 2 times h of n. So the corresponding output is 2 times h of n. Now when what we do, we will apply this as the input to the system. Now, how do we obtain this? First of all, how do we obtain this? We multiply x of n. What we do, we multiply x of n with delta n minus 1, and that's same as x of 1, delta n minus 1, and that is same as x of 1 is 1. So this is delta n minus 1. So how do we write it? So this is 0 when you multiply it with, so this will be, what is the value of given signal when n is 1? 1. So 1 multiplied by 1 is 1, 0, this is 0, this is 0, and the rest of the sample are zeros. So this is the so this is the input to the system. So we apply this as input to the system. The corresponding output will be h of n minus 1. Whose impulse response is h of n. So how do we write it? So we can write it like this. So what's this doing? This is simply shifting the h of n, the given h of n by 1 unit. So this is delaying. In short, this is delaying the given input by 1. This is simply delaying the given h of n, means the given sequence h of n by 1 sample value. So we'll have here 2. This will be 1. This will be minus 1. This will be 2. And this is 0, 1, 2, 3, 4 is 0, 5 is 0, minus 1 is 0. See, our h of n is simply this 1, 2, minus 1, 2. So the output of h of n minus 1 will be simply the shifted versions of these, simply the shifted version of this, and shift towards right. H of n minus 1 is simply shift this h of n by 1. So this is the output when the input is delta n minus 1. Same way to obtain, now our goal is next to apply this as the input to the system. Now how do we obtain it? We multiply x of n by delta n plus 1. So we multiply x of n with delta n plus 1. That will give us x of minus 1 delta n plus 1. Delta n plus 1, and that's delta x of minus 1 is 1, so it will be delta n plus 1 simply. So this will be 1. This is our input to the system. So input to the system is this signal. Rest of the samples are 0. Rest of the samples are 0. So you can say when the input is this, system whose impulse response is this, output will will be simply h of n plus 1. What is this operation? This is simply time advanced operation of h of n. This is time advanced version of h of n, and you can write it like this. So this is our h of n plus 1. And let's write the sample values. What's h of n? H of n is 1, 2, minus 1, 2. So you are just time advancing this by how many samples? By one sample. So this is 2. This is the value at 1. At value at this will be minus 1. This will be 2. And this will be 1. So this is the time advanced version of this sequence. So this is the time advanced version of this sequence. All right. Now, how do you obtain the total response? We said the total response we can simply obtain it doing the addition of these individual responses. So we do addition of this response plus addition of this response will give us the total response. Let me compress this. So the output will, you can write the y of n will be simply y of n will be simply over y of n, and y of n will be sum of these signals or sequences. So adding the corresponding sample values, we'll have at n equal to 0, this has 4, this has 1, this is minus 1, so that will be 4. So this is our 4. So n equal to 0, the value of the signal is 4. Similarly, the value at n equal to 1 is minus 2. This is 2, that will cancel. So this is 2, so it will be 2. So this is our 2 at n equal to 1. Same way, when n is equal to 2, this is 4, this is minus 1, this is 0. This is at 2 is equal to 0, this is 0. So this will be 4 minus 1, that is 3. So this will be our 3. At 2 n equal to 2, this has value equal to 3. Similarly, at n equal to 3, the value is 0 here, the value is 2 here, the value is 0 here. So it will be how much? 2, 2. So this will be 2. So this will be 2. 2, this will be 4. So next, what we do at n equal to 3, this is 0, at n equal to 3, at n equal to 4, this is 0, this is 0, this is 0. So you can say the rest of the samples are 0. Now at n equal to minus 1, the value is 2 here. At n equal to minus 1, the value is 0. At n equal to minus 1, the value is 2. So 2 plus 2 is 4. So this is 4. Similarly, at n equal to minus 2, the value is 0 here, the value is 0 here, the value is 1 here. So you can say this is 1, this is 4. So these are the values of the sequence. So this is our output sequence. Let me redraw this sample point. So this is our 1. So this is our 1 value. So this is our output sequence. This is how we obtain the output using the linear approach. This is the best illustration of this convolution. Please go through this 5-6 times. You will get this. Now, the same way you can obtain the output in sequence form. In sequence, you can do this operation in the sequence form also. Now, twice h n you can write in sequence form like this. So how do we write it? This is 2, 4, minus 2, and 4. And the n equal to 0 point is this. Same way, h of n minus 1 is 1, 2, minus 1, and 2. So this is n equal to 0 point. Same way, this is our h of n plus 1, and that's equal to 1, 2, minus 1, and 2. And this is when n equal to 0 point. Now what we are doing in this linear approach, we simply take the sum of these individual responses and we'll get the output, and we call that output as y of n, and let's write that. So first start with n equal to 0 point. This is 4, this is 1, this is minus 1. So it will be 4 plus 1 plus minus 1, that will be 4. Same way, at n equal to 1, this is 2, at n equal to 1, this is minus 2, this is 2, and this is 2. So it will be 4 again. So 2, sorry, it will be 2. It won't be 4, it will be 2. So the output is 2. So the output is 2. So this is our 2. Now at n equal to 2, this is 4. At n equal to 2, this is -1. And here we have 0, so it will be 3. Same way at n equal to 3, this is 0. At n equal to 3, this is 2. And this has again 0, so it will be 2. So these are the positive values. Now means when n is positive. So this is at n equal to -1, this is 2. Here it has 0 value. Here it has 2. So it is 4 and this n equal to 0. Same way, the value at n equal to -2 is 0 here. That value at n equal to -1, -2 is 0 here. At n equal to -2, the value is 1 here. So this is our sequence. You can see the result here and here are identical. So you can obtain this either graphically or in sequence form. So what is linear approach? What's linear? What we do, we express x of n as a linear combination or a linear or a weighted sum of these delta sequences. In other words, we apply the sample values of x of n one by one. And to apply the sample points of x of n one by one, what do we do? To obtain the sample values individually, we multiply this x of n with the corresponding delta n, and it is shifted versions. And we express x of n as a weighted sum of these delta sequences. Then we apply these individually. So we apply these as individually as input, this individually as input, this as input, and obtain these corresponding responses. Then we do the sum of these responses and we obtain the output. So we obtain the sum of these responses and obtain the output. And this we can do either graphically or in sequences form. I hope you understand this point. This is very, very important point. Please go through this. So the simple trick here is obtain the sample values of the sequence one by one, apply these sample values one by one, and obtain the corresponding response. And how do you do that? We go to the this impulse response theory. Means we say what is the impulse response of the system. If we know that, we can determine the output for any input. So this is the linear approach. In the next step, we'll do one more way to compute this convolution sum.